Welcome to Deep Engineering's YouTube channel, where we bring you real world insights from the architects and engineers shaping modern software. Today, we have the pleasure of having Imran Ahmad with us again, whose latest book with Packt, Architecting AI Software Systems, authored alongside Richard Diavila, is due for publication this November. Imran Ahmad is a data scientist, educator, and author focused on algorithms, AI, and cloud computing. He leads machine learning projects for the Canadian government, teaches at Carleton University, and is an authorized instructor of AWS and Google Cloud. He's also the author of several other books, including 40 Algorithms Every Programmer Should Know, published in 2020, 50 Algorithms Every Programmer Should Know, published in 2023, and is currently working on his next book, 30 Agents Every AI Engineer Should Know, which is expected to come out sometime early next year. All of these with Packt. Now, outside of his professional work, Imran has told me he enjoys photography and biking, and he also mentors developers through his Discord community and workshops. And we'll provide links to those under the video in the description below. So a very warm welcome to you, Imran. It's really great to have you with us again today.
Oh, thank you very much. Thank you. Good to see you.
Same here. So let's get started. And we're going to start with your book, which I believe is coming at a time when AI is becoming ubiquitous in software. We all know that. So I'd like to start by asking you, what inspired you to write Architecting AI Software Systems now? And what gap in the industry or knowledge are you hoping to fill with this book?
Okay, so let's start with the problem that we are trying to solve. The problem that we are trying to address here. So when you design AI systems or when you have a Gen AI solution, you have to have an end-to-end solution. So you have to look at that from in its totality. So what happens is that whenever there is a new technology, whenever there is a new idea, a technical idea that is there, so we start with focusing on depth. We develop solutions, we experiment with that, we iterate through different versions of it till we are ready to use that for solving large scale problems. Beyond solving those cats and dogs pictures, differentiating between cats and dogs. Now, AI has come a long way. Now, when we have gone through our dev processes, they have matured, then we need to deploy these solutions. So, and these AI solutions are only useful when they can solve a problem in production. And when you bring these ideas to production, then from start to end, they need to work properly. And around that, you have to design architecture. So I'll talk about this as well, that how do you quantify a good AI architecture? There are 5 pillars, as we call. I'll talk about that later: security, reliability, performance efficiency, cost optimization, sustainability, and something that is perhaps the most important, that is operational excellence. I'll talk about that later. But the need for this is that, bringing these ideas to production, that can only be done if you're giving it proper thought. We are bringing all the best design patterns to the plate. And this is something that motivated me to write this book.
Yeah, brilliant. And your book takes a very practical, architecture-centric approach to AI, isn't it? It mentions a structured journey with real-world examples, hands-on exercises, and even a fictional AI systems architecture as a learning tool. So can you give us a quick overview of the key themes or unique features of this book?
Yeah, so the way we have designed this book is that we have essentially divided that into 2 parts. And the first part is about the fundamentals of architecture. And now, if you look into the first part, the first part, zooms out and talk about in general, not very specific to AI, but in general, what are the principles for good architecture? And of course, we are talking about AI. But we talk about the fundamentals of AI systems, and this is where we define terms, we define microservice architecture, and we discuss a couple of actual use cases. And then we also define terminology like data lake, what is data warehouse, and why AI is so important in the context of designing AI systems. Because when we bring these systems to cloud computing, then you have elastic architectures. And as soon as you become elastic architectures, your system can become cost effective and performant at the same time. So, so if you think about this, so usually the performance system, they are not cost effective, they are expensive. It's like you buy a Ferrari. Ferrari is performant. It's one of the expensive cars, it's one of the fastest cars, but Ferrari is expensive. So we are trying to buy Ferrari at the cost of Toyota Corolla. So we want systems that are cost effective and performant at the same time. And elastic architectures get you there, where you can where your systems can expand and shrink based on the immediate needs. And this is where we talk about why cloud computing is so important. So this is chapter one. Then we talk about case of architecture. My co-author Richard, he's a great architect. This is where he brings his 30 years of experience here, and he talks about the role of architect, the vision, the style, and most importantly, he talks about that what are the implications if the architecture is not properly designed. So he talks about some examples as well. Then chapter three is about we bring software engineering into the picture, and we see that okay, what are software engineering specific topics related to architecture? This is chapter one. Chapter one is done. So part two is about AI systems. It's specific to AI. So what are the architecture templates? What are the architecture philosophies that are relevant to AI systems? And here we talk about something that is called concept of operations. And we talk about how concept of operation that is relevant to AI systems. And then we talk about, as you mentioned, certain use cases, large scale use cases. And we go over complete use case that if you want to design a RAG, then how we can use the ideas that we have developed in this book and how we can apply that to an actual use case.
Right, brilliant. And what kind of, if I ask you to just talk about two or three key skills that readers can expect to gain from the case studies and exercises, and also may perhaps changes in mindset?
So first skill is that how to convert an idea into a design. This is skill number one. So the requirements are requirements capture the idea, in a formal way. But now requirements are usually written by a non-technical person. You know. Now, the first part of the solution is that to convert those requirements into a technical design, that is the architecture. This is the skill number one that they will learn. Skill number two they will learn is that there may be surprises. Your design that you came up with may not be the perfect one. You have to iterate through that. So you come up with something and it may or may not work. And now you need to find ways that how to differentiate between a good design and a bad design. you know so functionally they will work. Functional requirements, they are met. They are the non-functional requirements that differentiate between a top-notch design and a design that is not that great. And now this is about looking at the how cost-effective your architecture is, how performant that is, how secure that is, how reliable that is, and whether you're using the principles of sustainability. And then are you bringing operational excellence? Excellence is a concept that we have discussed in this book. Operational excellence is that when you are designing these architectures, you are looking long term. You are using YAML files. You are using orchestrators. You are using JSON files. You are parameterize. You are using parameterization wherever possible, so that you can reuse them. You can maintain them easily, and you are again looking at long term. So this is where, the second skill they will learn is that your first attempt at the design may not be the best one. So you have to rethink, you have to evolve, you have to quantify that how good your design is. And then before you actually start implementing that, it's a good idea that you start with a pilot project. Pilot project is something that is usually 1/10 of the scale of the original project, but it actually covers all the critical points, all the critical design parts. It validates that, and then you basically go towards the full-blown solution.
Brilliant, brilliant. Thank you for that really in-depth dive into your book there. Now let's move on to our next segment and talk a little bit about key challenges in AI architecture in the current context. So many teams struggle to turn AI prototypes into reliable products. From your experience, what are the main challenges in bridging the gap between a promising AI demo and a production ready system?
Yeah, so there you can look at that from three aspects. So let's look into the from that, and that's a very important topic as well. That when you move towards an AI solution, initially, you feel that it's a silver bullet. It can solve any problem. So that is when you are experimenting with that. But the success of an AI project, it depends on three factors. So first is cost, the second one is performance, and the third one is accuracy. And let me explain that. So usually what you have is that you have things are, so if you're applying AI to an existing problem, so you already have an alternative solution. You know that things are already working. Now you are upgrading that, and you are bringing AI to the picture. You want to do things in the new way. So while you are moving to this new world, if I can call it, then first you need to quantify this, that what is the effect on the cost, whether the investment in the AI, there's an initial investment, then there are running expenditures. Can you justify them by the aggregated cost saving that you are expected to get? This is point number one. The second one is, I said performance, but it's actually time. Your current processes, whether they will be optimized in certain ways, whether the time to get things done, whether to meet some of the requirements, will they be done in a more timely fashion? Let me give you an example here. If it's a bank manager looking at people are applying for mortgage, and that bank application now wants to use AI, so perhaps instead of taking that bank manager 4 hours, it will take 4 seconds. Now this is the time that has been saved. So this is the second dimension. And the third one is accuracy. So whatever your current systems, current processes are, now this new world, the new ideas that you are giving through AI, whether that will be more accurate or not. So so you have to basically look at in these three dimensions, and you have to make some progress. Maybe it will be more costly, but if you can justify in terms of time and accuracy, then yes, you may be able to sell the idea to the senior management, right? And this is, I encourage that this is something that we should do right at the beginning. It should not be an afterthought that once I've seen that people come up with these AI architectures, and architecture is implemented, then they do some sort of time and motion studies and try to see, okay, whether we justify it or not. So you have already implemented, you have already invested, you have already using the system. So it's more like you buy a car, so let's say that you buy a plug-in hybrid, you've already paid the money, and then you go to ChatGPT and see that, okay, whether it made sense or not. So you need to basically check that before buying a car.
Right, right, absolutely. And how can software architects specifically help ensure an AI proof of concept scales into a sustainable real world solution?
Okay, now sustainability is done at two levels. If you are using cloud computing, then maybe it's not your job. This is the job of the vendor, AWS or Azure or Google Cloud, but still you can do a lot. So, for example, if you're using virtual machines, so even if you have subscribed to virtual machines, and it means that in all of these cloud offering, if you pay a fee, then you can keep running these virtual machines 24/7, and you still have to pay a flat fee. The same goes for the servers that you are running in-house. Now, what you need to think about this is that now these are performance hungry, power hungry machines. And number one. The second thing is that these days, a good design is where we design compute dimension is an ephemeral way. And the data dimension, so there are two dimensions when we talk about the architecture of these systems. There's a data dimension and there's a compute dimension. And the design pattern that we suggest is that, first of all, there should be clear bifurcation. So the data and compute dimension should be separate. Data dimension should be long term. It means that for 2 or 3 years, your data is stored there. Compute dimension should be ephemeral. It should be temporary. When there's a need to process the data, you provision the compute dimension, you process the data, and then you just suspend it or just remove it. There are a couple of, and let me give you an analogy here. So a simple analogy. So all of us, we work at our favorite word processor like Microsoft Word. Now, when you open Microsoft Word, the file is usually there. Let's say that you are working on a research paper. The file is there, and whenever you find time, you open Microsoft Word, you work on a file, you store it, and then you come back. Then you go back to your work. So the data dimension, your paper is stored for those 4 or 5 years perhaps on your hard disk. But compute dimension is your word processor. Whenever you want to change that, you open Microsoft Word processor, for example, Microsoft Word, you change it, and then once you're done with that, you close Microsoft Word. Now, we can have the same design pattern for AI systems. So it means that whenever there's a need to change, whenever there's a need to train a model, whenever you need to change the processing pipeline, or you want to process the data, in that case, what you do is that you provision your compute dimension. So compute dimension should be need based, and the data dimension should be long term. If you follow this clear bifurcation between data and compute dimension, what's going to happen is that our AI system, it will be cost effective, it will be performant, and it will also meet the needs of sustainability as well.
Brilliant. Okay. All right. All right. Okay. So, Imran, there's a concern about the sustainability and vendor lock-in of today's AI platforms. For example, OpenAI reportedly reached 10 billion in revenue, but is losing around 5 billion a year, a situation some have dubbed a subprime AI crisis. Now, if enterprise architects build around such providers, they face continuity and lock-in risks. According to you, how should architects mitigate these risks?
Okay, so wherever there's a choice, do not use the proprietary vendor specific APIs. So almost always we have two choices. You can use the vendor specific APIs, or you can use a higher level generic API. And I'll give you a specific example. So when you are working with large language models, you can use the APIs that are provided by OpenAI. This is choice one. Because you were talking about OpenAI, so let's go with that example. Uh, the second choice is that you can use LangChain. LangChain is an orchestrator. Now, LangChain, if you use LangChain API, then what will happen is that your code will be talking to LangChain, and LangChain will be talking to the OpenAI specific API, right? Now, let's look into the scenario. Unlikely, but can happen. Let's say that OpenAI goes bankrupt. And now, so the connection between LangChain and OpenAI, that will change to perhaps LangChain to Gemini or LangChain to Claude. So that is all that is needed. So your code is not dependent on OpenAI. Now, this design pattern you can repeat that for the clouds as well. So, for example, if you're using cloud, so if you use open source APIs, then it means that let's say that you are using Docker containers. If you're using Docker containers, then your cloud computing is just a living space for your Docker containers. If you're using Kubernetes as an orchestrator for Docker containers, that is even better. So it means that all you need is that your cloud computing platform, it becomes a Kubernetes enabler. Now, if one of those enablers goes bankrupt, all you need to do is then move to a different one, and you don't have to change even a single line of code. But in this approach, we have issues as well. So, for example, so all these vendors sometimes they provide the best tools in their vendor specific APIs. I'll give you an example here. So, if you use Google Cloud, one of their most polished tools that is called BigQuery. You know, now BigQuery is vendor specific, and for AWS that is Redshift. Redshift is vendor specific. Now, but my recommendation is that still the risk of being hard coded to vendor specific tool, that is more, that is, and at this point when things are changing so fast, we should be cautious and we should be putting effort at being as much as vendor agnostic as possible.
Right, right. And would you advocate for designing for provider agnostic AI services right from day one, or even using open source models and hybrid AI architecture? Perhaps, what's your view on all this when it comes to balancing control and convenience?
Okay, so open source models, they lag behind the functionality of closed source, right? So what I would advocate is that use open source APIs, right? So that your code is not dependent on the proprietary models. Open source models, they have their place. Llama is an example, or DeepSeek is another example. Now they have their place if you're talking about large language models. But sometimes we want to get latest and greatest, like the work that OpenAI is doing. And usually open source models, they are a generation behind because of all sorts of reasons. So what I would advocate for is that use vendor agnostic APIs. If possible, use open source models. If I'll give you an example here. So when we deal with text these days, so one of the problems that we face is that which model we should use for embedding, right? Word embedding, for example. Now, for word embeddings, the trend these days is that why don't we use one of the models like BERT or GPT for word embedding, instead of using Word2Vec that we used to use 5 or 10 years ago. Now, for for these solutions, we can use an open source simplistic model, right? And once we have done the word embedding, that is part of our RAG pipeline, then we can go towards a proprietary model using the open source APIs. So we can mix and match where we shouldn't over design and we should not under design. That's the thing. So wherever an open source model fits the need of part of our solution, let's use that. And whenever there's a need that we need to use a proprietary model due to its functionality, due to the additional power it can provide, use it, but use it through an open source API. Try to
Yeah.
not use the vendor specific API wherever possible.
Right, right. Okay. Next question. Ensuring quality and maintainability in AI software is an emerging concern. And studies have found that many AI ML code bases have minimal testing and documentation, often due to lab style development by data scientists. And according to the State of Software 2025 report, only 1.5% of the code in AI big data systems is test code versus 43% in traditional systems. Um, why do you think AI projects often end up with weaker software engineering practices?
So it's a new technology, right? So the because the thing is that in many cases people are learning as they are implementing, right? So this is a byproduct of that. Well, whenever there is a new technology, as compared to a mature technology, for mature technology, the test cases have already been established, right? So we know that for other similar projects, so this is the criteria of success, in functional and non-functional way. So when there is something new, it's working. So then we need to ask ourselves that what is the best way of test its functionality. Now, for example, if hallucination is a concern, so how to test whether our solution is hallucinating or not? If accuracy is a concern, then how to test the outliers in a Gen AI solution? This is they are the first of all the metrics, they are still evolving, and testing is all about quantifying that our solution is meeting the agreed upon goals or not. Now, those agreed upon goals, they are still evolving, and that is one of the reasons that there is you are quite right here that these projects, they are not well tested. Yes, that is a concern, but things will improve.
Right. And what can architects, now being aware of it, to instill better rigor? For example, would organizing cross functional teams of data scientists and software engineers help bridge the gap, or is it something else?
AI is quite subjective in different ways. So it means that a project may be successful for me, but for you, it may be a failure, right? So there is some subjectivity there. And as you brought up a very good point, one way of mitigating that is that, coming up with a consensus with the people with different roles, with different skills, a data scientist, data engineer, a project manager, and perhaps a business analyst, a person who is basically in charge of production. They will have different views of the success of a project. Data scientist is for a data scientist or an AI engineer, the success is mostly about meeting the functional requirements. For a person who is in production, he has no idea of algorithms. He has no idea of what is ROC curve, what is AUC curve, what is recall, and what is precision. For him, the success is, putting the Dockerized solution on a server and making sure that non-functional requirements of reliability, security, performance, and availability. So for that person, that is the criteria of success. If it's a if it's an application for approval and refusal of a mortgage application, the person who is in production, for that person, it's all about the service is available or not. But for the data scientist, he will all be concerned about the metrics that are concerned that are more related to data science. So we have to bring them to the table and come up with the consensus that, okay, how does the success of end-to-end success of this project will look like, both in dev and production.
Great, great. And do you almost feel like bringing them to the table in this kind of, you could say, sort of multidisciplinary way is easier because of AI now?
So let me give you an example that ideally what we should be doing. So anyone who has taken an advanced course in prompt engineering, right? In prompt engineering, we have one of the techniques that is called tree of thought. There's a chain of thought, and that is tree of thought. Because I'm writing a book on agents, so this is something that I was working on recently. So tree of thought is that when you are coming up with um, with the solution for a complex problem, then what you do is that you create those virtual specialists. I'm talking about prompt engineering, not the actual world. So we create those virtual specialists, and let them argue among themselves. Let them discuss the idea. And let me give you an example here. Let's say that you're using cloud computing. Let's say you're using AWS, and you want to reduce the cost. And that pattern, tree of thought, what it does is that it will create typically three virtual experts. One is a technical person, one is project manager, one is perhaps a data engineer. Let them argue, let them, argue in a respectful way. And if you follow that pattern, it will show you the discussion, the virtual discussion that happens among them. And then at the final step, they come up with consensus. And, and consensus is a compromise, right? Now, this is again, I was talking about prompt engineering, one of the concept that is called tree of thought, to come up with the consensus through extensive reasoning coming up from the virtual experts. We can apply the same idea to the physical world as well. Whenever there is a problem, if so, people do not have to agree on everything. So they have to speak out that what do you think about the solution, and then they discuss, they understand each other world, and then they come up with a consensus, a compromise. And once that is made, then you follow that for the criteria of success. This is something that needs to happen, especially for large scale projects.
Right, right. And I think that brings us nicely to our next section where we're going to talk about designing scalable and robust AI systems. Um, Now, AI systems must be built with scale in mind from the start. On the training side, deep learning models demand substantial compute, GPUs, TPUs, etc., and efficient distribution of tasks. On the inference side, serving many users requires horizontal scaling, containerization, and load balancing to keep latency low. According to you, what are some architectural strategies to handle scalability for AI?
Okay, first of all, it depends on the problem that you are trying to solve. The scalability requirements are different for different problems. And let me give you an idea here. That let's say that first of all, when you are training a model, now this is where the most cost are incurred. You know, so it means that you need GPUs. GPUs you use are expensive. You need CPUs as well, and then you need to experiment. You need to train over and over again. But the scalability requirements at dev, it has first of all two characteristics. Number one is that once training is done, you do not need those resources anymore till you need to retrain the model, right? So it means that if you are developing the solution for 2 or 3 or 4 months, and then your model is trained and it's in the production, till you need to retrain the model. So all those 20 machines that you brought, they will sit there doing nothing. This is the point one. That is why cloud computing is really good there. You can provision resources, and once you are done with that, you want elasticity becomes important. That is point number one. Point number two is that there is no deadline associated with the training process, right? So what it means is that at inference, there is a deadline. If it's a credit card, you swipe your credit card, and the fraud detection results need to come back within 5 seconds. Otherwise, if it's if someone is paying at McDonald's, swipe the credit card, that person cannot wait for 40 seconds. So results need to come back within such. In training, when you are training the model in dev, there is no hard deadline, right? It's more about your comfort factor. So if you can live with evolving the solution, scale down solution during the daytime, and at night time, you can try this out. Before you leave for home, or your team leave for home, you can keep it running, and you come back in the morning, and now the solution is there. During the daytime, again, you work on a scale down system. It's like 1/10 of the size, and you evolve. And before, if you follow that pattern, you can save lot of cost, right? So what it means is that now this is a pattern that we follow. At work, we follow that. What we do is that, and it goes a long way in saving the cost, right? So you use the night time for training, and in that case, again, we can use much lesser number of resources. So you need to be innovative. You need to be creative there. This is point one. The second thing is that let's talk about inference now, about scalability as applied to inference, right? The second part of the equation. Now, let's say the model is trained and now it's put in production, right? Once the model is put in production, we need to carefully quantify, analyze the requirements, the scalability requirements there. We shouldn't over design, we should not under design. Let me give you a couple of scenarios here. So let's say that that is again the example of a credit card, and each time you swipe the credit card, the results of whether it's a fraudulent transaction or it's a regular, it needs to come back in 2 seconds. It's a hard deadline, right? So you have to make your servers performant that they can meet that deadline, right? On the other hand, let's say that this is essentially a bank manager, and at the end of the day, he needs to just look at the spreadsheet that the transactions that went through during the day, how many of them were likely to be fraudulent so that they can be looked into. The requirements are at the end of the day, right? So in that case, we do not need to have the real-time endpoints there, right? So in that case, we can live with the batch mode for inference. We can save a lot of cost. So again, I said that, so in that case, what's there is that you do not need to provision endpoints, real-time endpoints. HTTP endpoints are not needed. All you need is that you just gather your unlabeled data and you create a batch of it. At the end of the day, top of the hour, end of the week, whatever granularity works for you, you submit that to the server. It basically creates the label that how many of them are likely to be fraudulent, how many of them are not, and the sheet comes back. So real-time inference is not needed. If you are doing it, it's expensive and you're over-designing the system, right? So the scalability requirements, in order to get to that, you have to carefully first analyze that, and based on that, design and architect your system.
Right, right. Brilliant. But now integrating AI into existing enterprise environments can be quite tricky. And sometimes the best approach is to deploy new AI capabilities within the customer's current on-prem infrastructure, so as to leverage existing investments and avoid disruption. But other times it may be better to migrate to cloud platforms to gain scalability and access advanced AI features. How do you evaluate which deployment strategy is appropriate for a given project?
Okay, so there are two things here. First of all, what I suggest is that we carefully determine the maturity level. So there are four maturity levels that what is the and maturity levels is about the technical infrastructure maturity and the skill maturity level as well, right? The people, let's say that let's imagine a company that, so there are 30 people working in that company, and let's say that they are working on developing a product that deals with it's a recommendation engine that they are recommending products to their existing customers, right? And they're using some algorithms, but now they want to basically modernize that. They want to use deep learning. They want to use Gen AI. They want to use to cloud computing, right? First thing that then the requirement is that they cannot afford any disruption. So first you need to look into that what is the maturity level of their existing infrastructure, right? So what they're using, which tools they are using, and what is the skill level of the people that are working on that product if they don't plan to hire new people, right? So we have to use the existing infrastructure and we have to use the existing people, right? Then we have to develop the phased approach. Usually there are four phases. So phase one is that we just come up with a plan, looking at the current situation. Okay, that this is the current situation. Then what is the plan forward? This is something that we start with. The phased approach, what we do is that phase one, what we do there is that depending upon the maturity level, we'll say that in the phase one, we will what we'll be doing is that we will be moving we're identifying that okay, perhaps accounting can stay on premise, but perhaps the algorithms can move to the cloud. So this is one thing that we can do. Now, and then we have to figure this out, that how we are going to create a pipeline that can link the on-premise with the cloud. So usually what we do is that we keep redundant systems, both on the cloud and on-premise. And slowly what we do is that we test that and then we remove that. So this phased out approach is, it will be vertical dependent, it will be company dependent, and it will reduce the risk, and that usually works.
Okay. And so, if I said in summary, what factors should influence whether you keep AI systems on premises versus in the cloud or a completely new environment?
So, for in some cases, we do not have a choice. If you're working for a government, if you're working at a financial company, there are regulatory requirements that your data cannot be on the cloud. So there are many companies. There are three sectors usually: government, healthcare, and financial industry. And now these three are, and some of their data, it needs to be compliant to the existing regulations, and it's not impossible, but it is more difficult for them to bring the data to the cloud, right? For government, sometimes it's not even possible, right? Now, this is one thing. Sometimes what happens is that companies, they're using legacy systems. I'll give you an example. There is a tool by IBM that is called IBM SPSS Modeler. Now IBM SPSS Modeler, there's their version of SAS. Banking industry are still using that. Now, if your processes are dependent on that, it's working fine. You will not like to basically move to a new system because it's working fine for you. But in that case, if the cloud version is not available, so now you are tied to your legacy system. Unless and until you are ready to retire your legacy software, there is no way you can move to the cloud. Then sometimes what happens is that in the cloud is, I'll give you an example here. So Canadian federal government, about 4 or 5 years ago, they thought that they will move to the cloud. Canadian federal government, its infrastructure is huge. If you just look into the amount of money that is spent on the infrastructure to support the Canadian federal government, you can look at that. It's billions of dollars, right? So they thought about 5 years ago, just before COVID, that we will move all our services to the cloud. And the study was that it will save about 20% of the cost, right? That was the initial study. Now, 5 years down the road, it didn't happen. They moved to the cloud, but instead of cost being reduced, cost has increased. Right? And so the dream was that federal government will save 20% of the money. Cost has increased by about 12%. That is the number, right? And there's a reason for it. The reason is that reason is about architecting the system. So when you're designing the systems, and if you're in a hurry, and if you don't make a conscious effort, the simplest of the architectures in cloud, they are not cost effective, they're not performant, they're not elastic. You know, you let a virtual machine run 24/7, it will meet the functional requirements, but it is not elastic, but that's the easiest solution, right? So you have to take a step back and you have to think it through, that okay, let's spend some time on the architecture. And that this is where in the book we have talked about the case for architecture, taking a step back, spending some time there. Because in the long run, I gave you the example of Canadian federal government, it will save you lots of money, right? Because if you have already, in a hurry, if you have already started with something, the easiest possible solution, it will be many times difficult to refactor that 2 years down the road, when you have already started your computing resources. You have already have your compute dimension, data dimension, functional running. Now you want to change it, it will be very difficult, it will be risky, it will be, you are again doing something that you should have done a couple of years ago. That is why, there's a whole section on our book that talks about the case for architecture, why we should, what is the need for the system architecture for AI systems.
Right, right. Now, switching gears a little bit, user experience is a critical yet often overlooked aspect of AI systems. A technically brilliant AI solution can flop if users find it confusing or don't trust it. How can architects ensure an AI system delivers a good UX and drives user adoption?
Yes, so for our use, so we should always be designing the system. We should always be thinking it as a service. That, if you're a technical person and if you have a spouse who is non-technical, just if you have a spouse, so or if you have a brother or a sister who is a non-technical, think about that person, that whether that person can use the service or not. So my brother is a medical doctor, so I always think that okay, the service that the eventual service that I will provide, can he use it or not? So sometimes what's there is that we bring those technicality to the user experience as well. So we spend so much time in the technical aspect of it, so we forget that our end user is a non-technical person. He shouldn't even need to know that what was the details in the data dimension or a compute dimension, how we are designing the pipeline, whether it's an elastic infrastructure or it's so which algorithm we are using. So that all should be a black box once things are done. So it's a good idea that always try to see from the eye of a non-technical person how easy it is for a non-technical person to use it as a service. So think about it as a service. So your solution, it should be, so there are different Zoom levels. You can think of your solution as a microservice architecture. Now, microservice architecture is quite technical. It's great for providing abstraction to a data engineer, but not to the end user. We need to use zoom out more. Because I'm photography, I'm giving examples from the Zoom level. So zoom out more, and so just think about it as a service.
Right. Really great insights there. Can you think of any best practices for aligning AI architecture with great UX design?
Yeah. So the example of that is that let's assume that sometimes we are using AI without noticing it. You know. So let's talk about this as well. The greatest example of that is that when you use Google Maps, when you use Google Maps, now Google Maps uses basically an optimization algorithm, right? You go from point A to point B. If you look under the hood, because my PhD was in algorithms, so optimization algorithms are one of the hardest. So there is a famous example of traveling salesman's algorithm. And traveling salesman's algorithm, this is basically that if there's a person or a traveling salesman needs to visit city 1, city 2, city 4, this is an NP hard algorithm, right? So it means that whenever you say, okay, I want to go to my office, you enter the address and you press basically, direction and start. You don't know that under the hood, there is a lot that is going on, right? So first of all, your GPS location that needs to be tracked, that needs to be communicated to a backend server. The algorithm needs to be triggered between your current location and the destination. And if the traffic location, the traffic situation needs to be there, that what are the real-time traffic situation from your source to the destination, that needs to be taken into account. And as you start moving towards your destination, the traffic situation can change, and it means that it needs to be dynamic in nature as well. And you read the destination, and then it asks you for a feedback. And we don't even realize that how much AI is used, how much real time information is used, and how much effort is how much computing power is used as well for this simple. Now this is the best example. People use it. My daughter can use it. She uses it to go to her school, but she does not even realize that what's going under the hood. That's the best example. When we are creating these solutions, they should be as simple to use, and we don't need to know that actually it needs to be effective. People will use it if they find we use Google Maps to be very effective. I don't need to. I know that where they will not work because I'm into algorithms, but there are some gaps there. There is no solution that is perfect, and I'll tell you the gap there as well. That I talked about. I talked about that in real time. It needs to know that where traffic congestions. The problem is that traffic congestion, the way Google collects that information is that it assumes that people are carrying those devices in their car, and if those cars slow down, it means that there is traffic congestion. It works most of the time, but where I live in the north, there is a Getnu Park. There's a Getnu Park. It's an 80-kilometer long. Is on their bikes, on their cycles. So they are biking in the Getnu Park, and their GPS devices, Google Maps, they are using it. And Google Maps always think that there's traffic congestion. It's always red. But if you go there is no one there. So there will be failures. It's not that algorithms always work, but we don't need to know that. Most of the time it will work, and the best user experience you get from there, and we don't need to know what is under the hood.
Yeah, right. That's a very good example. Thank you for that. I always look forward to your analogies and examples, Imran. Now let's talk a little bit about trends and see if we can, predict the future a little bit. So the rise of agentic AI, which is a hot topic. And we spoke earlier this year and, we talked about this, we touched on this and how 2025 is the year of the agent. Now, major platforms are jumping in. For instance, Microsoft's new Azure AI agent service helps orchestrate multiple specialized agents as microservices. What does this shift from single model applications to multi agent systems mean for software architects?
Okay, first, let's think about this that right now. So, let's say that what is an agent? I know that you can find so many examples on the web, but let's try to think about this. So, what we are trying to do with the AI system is that we are trying to mimic the human wisdom, right? This is all artificial intelligence is mimicking the human wisdom. So let's assume that my manager comes to me and wants me to solve a problem. She wants me to solve a problem about, let's say, that wants to develop a fraud detection system, and she wants to get it done by the end of Monday, right? And the requirements are there. Now, I have no idea how to do that at that point. She said, Imran, this is what needs to be done. Can you complete that by the end of Monday? So first thing what I'll do is that I will try to discover that, okay, what are the requirements and what are the tools that are available. So there is internet available, there is chat GPT, there is Google, there are some books available because I teach at university. So I can go to those research papers and I can look into that. I can ask a friend, or these are tools available, right? So in my mind, I will orchestrate. I will use those tools in different ways. I will perhaps go to Google, couldn't find any information there. Perhaps I'll use ChatGPT. I'll try to write some code, and subconsciously, I will orchestrate a plan. I will start using those tools. Some of those will work. Some of those will not work. And my solutions that I will deliver at the end of Monday, if someone is crazy enough to record me, it will be a trial and error. It will be orchestrating or using the existing tools, being aware of the tools that are available to me, and coming up with something that is in a meaningful way. Connecting them in a meaningful way till I get to a solution that satisfies the requirements. Agent is this. If software can do that, agent is this. Agent is mimicking this human behavior. It is aware. Ideal agent, it should be aware of the tools that are available. It should be capable of using these tools in a way that we can come up with a meaningful solution. And number three, it should be ready for the surprises. just like I mentioned that my manager came to me, I thought that Google will give me good results. It didn't work. I have to change my plan. So it should be dynamic enough that it can change. It can replan as it go. So now these are three attributes of an agent. So we are bringing wisdom outside of large language model. Current GNI solution, all the wisdom is in the large language model. So in an agentic system, large language model is one of the tools. It is one of the important tools, but is right now the king becomes the agent. King is not the large language model. So this is something that it's an exciting world. You talked about what Azure has provided, and Google has also its own solution. There is something that is called agent space. There is agent development kit is there. Azure has come up with their own things. AWS is lagging behind just a bit, but they will catch up pretty soon. But these are all doing the same thing. If we can zoom out and look at them from a vendor agnostic manner, so all of them are doing almost the same thing.
Right. And how do you think architectures may evolve to accommodate this, network of AI agents that can plan, collaborate, and act unanimously?
Okay, so first of all, architects should be aware of these new developments, right? It's not easy to keep up with that. They need to, so if you try to learn everything, you end up learning nothing, right? So you you need to pick your battles, that this is my area, right? And that is why this book is about the architecture of AI systems. So we think that as we progress through in the later part of 2025 and 2026, AI architecture, that is now becoming a specialty, right? So you need to be aware of these developments, and they are coming on daily basis. So the best way I can keep up with this is that first of all, subscribe yourself to good YouTube channel. That's a tip I can give. YouTube channels, good quality YouTube channels. YouTube is filled up of people who just read an article and then they come off a microphone and they just give a talk. And they don't know anything about what they're talking about. So first of all, high quality content on YouTube, this is your best bet. Now, so first of all, be aware of what the decent development. The second thing is that what is relevant today may not be relevant at the end of 2025. This is one thing, right? The second thing is that the good news is that 80% remains unchanged. 80 to 90%, this is the basics remains unchanged, right? The need for elastic architectures, the need of reliable architectures, the need of performant architectures, the need to create orchestrators, to need to create operational excellence, to have data and compute dimensions, to have bifurcation among them, and the need to move towards cloud platform, and the basics of that, they don't change. This is only the 10%, right? If agentic systems are, this is not the only way of doing. If there is a new way that is coming, you should keep yourself open. Of course, this book will cover that 90%. So the 10% will be dynamic. You should keep your mind open, and keep incorporating new ideas as they come along.
Right. Right. So you've got people covered by a book, but what challenges should we be prepared for in areas like agent coordination, security, or reliability?
Okay, so those challenges, just like Kubernetes. So let me give you an example from Kubernetes. So when Kubernetes in initial days, so maintaining a Kubernetes system was a job of its own. Because I teach, so the courses that we create for Kubernetes, they were so much in. People just want to learn that how to design a Kubernetes system, how to maintain, how to babysit a Kubernetes system, right? Now the Kubernetes has matured. So in fact, I'll give you an example here that if you use Vertex AI and if you use Vertex AI pipelines, under the hood, it provisions a Kubernetes system for you. And you are not even aware of that it's a Kubernetes provision of Kubernetes. You just use it. So right now, these agentic systems are the Kubernetes of early days because they are being developed. So you have to babysit them. You have to figure out that how these agents will talk to each other, MCP protocol, A to A, all those things. You have to do it by hand. You have to hardcore. Sometimes they will work, sometimes they will not work. But you will see that in less than a year, these systems will become mature. So as an architect, our job is not to figure this out, that how agent will talk to the other agent. We should not be getting ourselves involved in that. That should come out of the box. So these are agents, they should talk to each other. This is more about using the system. But because they are in early days, you will see those glitches that are happening. That's why we have to debug it. We have to be aware of that. But you will see that in coming months, these things will. It's more about be aware that this is multi-agent systems. Each agent is a specialist piece of wisdom that can handle a vertical. It's capable of handling a vertical. We should be aware of that, and we should be aware as an architect. We should be bringing those entities to our architecture. Let system evolve and mature in coming months, and those glitches will be resolved.
Right. Now, enterprises also grapple with how to integrate their data with AI models effectively. One common pattern which you've mentioned before is RAG, where the system fetches relevant company data to ground the responses of an LLM. But we are also seeing some new approaches, for example, Agentic RAG, and even using models with massive context windows to load whole data sets directly. How should an architect decide on the right approach for infusing domain knowledge into AI systems?
Yeah, RAG is becoming obsolete. You're right about that, but there are better technologies that are coming. There are advantages and disadvantages of all of them. So context windows are, becoming larger and larger, and that removes the need for a RAG. But it also means that with each request, you have to, if context is huge. So the advantage of RAG is that it only brings the right vectors or the right text. It only attach the right text. Yeah, it can do that. So our request is more efficient. It does not attach unnecessary text. If I am responsible for doing that, I will attach a whole book, as a context and send it to large language model. That may not be the efficient use of it, right? So RAG is more efficient. Agentic RAG is a step ahead. This is something that is still work in progress. They are not in production. These systems still struggle, but RAG will become obsolete eventually. And this is why I was saying that these systems are expected to evolve. So now RAG, you can think of RAG as a baseline system, and you need to understand RAG in order to get to the agentic RAG. So we in the book we have talked about RAG, and I feel that this will remain the evergreen example. Although RAG is becoming obsolete, because that is basically you need to first learn the simple use case before moving to the more complex one. Now they are coming back to your question. There are always more than one ways of doing the same thing. This has been always the case, right? In order to meet the same functional requirements, you can come up with agentic RAG. You can have a large context window. You can have the classical RAG, if I call it classical, or you can live with the prompt engineering. That is also possible. Extensive prompt engineering. And in many cases, there's an overlap in functionality. In that case, it becomes subjective, but you have to carefully see that what are the advantages and disadvantages. And based on that, you have to come up with the best solution that is available currently.
Right. And so finally, let's talk about the evolving role of the software architect in the AI era. It's been said that the AI architect is no longer just a technologist, but also a systems orchestrator and strategic partner in delivering AI value. How do you see the role of architects changing as AI becomes a core part of software systems?
Yeah, so the traditional architect was basically when we used to have that waterfall methodology that then clearly defined phases. Your project get approved, it gets funding. Here comes, then someone writes the business requirements for you. Then the project is signed. Then there's a red tape. After that comes the architect, designs a system for you, and whatever that person designs, they are written in stone. And then the technical team needs to implement that. And then the criteria of success is meeting the or implementing the design in the most precise way. Now, gone are those days. And the reason for that is that your architect needs to be involved in the iterative process. I mentioned that you will try something and sometimes ideas will not work. So it means that the role is more dynamic in nature. As you mentioned, that your architect needs to be involved first of all, it needs to be aware of some of the technical terms. Architect needs to be involved in the pilot project. It may need to refactor, it may need to redesign the data dimension, compute dimension, if there are performance bottlenecks. So it has become more agile. But the need of software architect is there. It's very important. It has become more important than ever. And let me give you the reason for this. So, large scale project is like building a home, you know. So now you can see that for building a home, in villages, they still build a home on the fly. They will say, okay, especially in certain parts of the world, what they do is that they have bricks. They have an idea that, well, let's build a room here, let's build a room there, let's have but in an organized way, an architect basically first plans that, okay, this is the home that we want to build. It gets approved, it goes through different iteration, and then we start building the home. But just think about this, that if the architecture is wrong, right? So let's say that the bedroom was supposed to be on the ground floor because the owner has a knee problem, cannot climb the stairs. But now the problem is that the bedroom has been designed on the top floor, and now the home has already been built. Now there's a problem there. There's a fundamental problem. It's almost impossible if to change the plan now. The same goes with large scale architecture. The basic templates need to be decided before you build the system. When we talk about that agility, that is about the fine tuning. Right? So that is why there needs to be an architecture that design the large scale components of it, and then someone starts implementing that. And there are companies, there was if someone wants to look into that, JP Morgan, you will find that in the news. JP Morgan, they designed their system and they spend minimum time in architecting their system. And then they were using proprietary systems. They wanted to go to open source. They didn't pay that much attention or time in designing the system. They picked such, for example, they picked MongoDB, other components there, and then they go ahead with their design. And 8 months down the road, they figured out that this was not the database that worked for them. Just think about this. It's one of the largest companies that 8 months down the road, they figured out that this was the wrong choice. And there was lot of loss of revenue, loss of time. And this is something that we want to avoid. Yeah, all forces.
Right. And last question to wrap things up. What new responsibilities or skills do you feel architects should cultivate now to successfully design and oversee AI-enabled software in the coming years?
Yeah, this is essentially making yourself aware of what technologies are there, but you need a bit more depth in the AI concepts, right? It should not be, you should be, so your ability to choose the right AI components, right? That under these requirements, what components are relevant. And for that, I think the training, making yourself a conscious effort to keep going in retraining yourself in AI, because AI for many architects, that may be a blind spot.
Right. That brings us to the end of our conversation today. Imran, thank you so much for joining us and sharing your deep and rich insights on architecting AI systems. It's been really great having you here with us again.
Okay, thank you much, and thanks for talking to me.
And to our viewers, thanks for watching. If you'd like to go further on the topics we covered, do check out Architecting AI Software Systems by Imran Ahmad and Richard Diavila. It's your definitive guide to building AI-enabled systems, emphasizing the balance between AI's capabilities and traditional software architecture principles. You'll find the link in the description below. Until next time, this is Divya for Deep Engineering.